Welcome to lecture 17 of Physics 1A. We're going to be covering the topic of center of mass. This is section 8.5 in Young 14th edition. And this topic is going to introduce the concept of objects in physics that are not simple particles. In other words, objects that have length, width, and depth. This is going to be a significant segue to the topics of chapter 9 and 10, where we discuss rotating bodies, which, if they're rotating about their center, they need to have a center of mass that's defined. So that's why this material is included with that rotational material and is not going to be on exam 2, because exam 2 does not cover the topic of rotation, either dynamics, kinematics, or energy of rotation. None of that is covered on exam 2. So let's get to defining the center of mass. So there's a few things to say about it. I will start with a colloquial definition of the center of mass that says it's the balance point of the mass distribution. So that's not a very technical definition, but it does help us understand it. And of course, for us, our most technical definition of the center of mass will be the calculation that we will see both for systems of objects like particles that are in a orientation to each other, or perhaps you can think like two planets, or also continuous objects, solid objects like cones and rods and spheres and so on. Okay, so another way to think about the center of mass, it is the point of an object that follows a path of a particle. So it is the point of an object that follows the path of a particle. And you might ask, what particle? Well, it's the particle that the object would be reduced to. So if I had a complicated object like a human body, and I wanted to find out what trajectory that human body was taking through the air, maybe someone's jumping, then I would have to track that body's center of mass, because that would give me the typical parabolic trajectory as if the body was reduced to a single particle. So that's a big functionality of the center of mass. Okay, so the other idea about the center of mass is it has some important direct applications. So I guess one of which is the path taken by a particle replacing the object. But the other is that it is the only point on an object where the gravitational force vector is applied. So that's a very important thing to remember when you're solving problems for objects. And I say objects as contrast to particle. So it is the only point where the gravitational force vector is applied. And often you still have to take into account what direction that vector goes, if the body is tilted in some way, usually relative to something else, like a ramp, right? However, it's a very, very important rule to stick to. And of course, it's something that we did not have to worry about before, because whenever we drew a gravitational force vector or any of our typical vectors, the normal vector, the tension, we didn't care about where that vector was located, because although we were drawing a picture that may have showed a block that had length and width, those length and width were never considered, because the block was not able to rotate. It was only able to translate. So it couldn't say tip over relative to its own center. So in functionality, despite being drawn as a block, it was a particle. Now, however, tipping, rotation about an object's own center matters. We've gone from particle to object. So hopefully that idea makes sense. I know I've said it in a few ways. So the last thing I want to say about the center of mass is just a kind of a word of caution. So I'll write it as a note. So the center of mass does not necessarily have equal mass to each side of it. So have equal. Okay, and this could be envisioned as two-dimensional or three-dimensional. Perhaps it's good to think of a two-dimensional object or an object in profile. And I bring this up because in some sense, this is almost the most important way to think about the center of mass in what it's not. I feel it's the topic that often comes up the most. So I bring it up because I've seen it confused many times. And because it's easy to think that, oh, the center of mass means just that it's literally the point where there's 5 kilograms of mass to one side and 5 kilograms to the other, because it's the center of the 10 in that case. But that's not what it means. It's the balance point. So to really consider that is you could just consider an object that has a very, very long handle, like a hammer, but with a very long, long handle, and then has some sort of head on it, right? And so this is the top of the hammer. Maybe it's made out of metal. Maybe the handle is not. Maybe the handle is made out of wood. But the thing here is, despite this being the lighter part and this part being a much bigger concentration of mass, the light part is going to have a big effect. If the handle is long enough, the center of mass could get pulled somewhere over here, for example. Okay, and of course we'll show how that's calculated. But in that case, the light handle over here, the mass of the handle could be far less than the mass of the mallet, the head of the hammer. So the head over here. So those two masses can be absolutely unequal. It's just that the handle has the advantage of being stretched out so much that it's pulled that balance point. It's pulled this X to mark the spot, the center of mass. It's pulled it away. Okay, and here, of course, I'm using a shorthand for the center of mass with the acronym COM, center of mass. I often refer to it as COM. So, but the point is that there's so many systems, if you do stop and think about it, where the center of mass would definitely not be really have equal mass to either side of it. Another good example is Earth and the Moon. The center of mass of the Earth-Moon system is near the surface of the Earth. That means to one side of that center is almost the entire mass of the Earth. To the other side of that center of mass is just the mass of the Moon. But the Moon is so far away that although its mass is much less, much less than the mass of Earth, about an order of magnitude less, so less a tenth, less than a tenth of the mass of the Earth. Its distance away has moved that center of mass, has moved that balance point. Okay, so I think we have a good working definition of the center of mass. Let's take a look at the calculations. Okay, so the first set of formulas that we're looking at under our key formulas are the ones that all have a big summation symbol. And all of these ones represent the beginning idea of the center of mass. And that is that if you have a system of discrete particles, okay, so this set here would be for a system of discrete particles. And all I mean by that would be discrete particles like Earth and the Moon, whereas the hammer that I drew above, the hammer up here, would definitely not be a system of discrete particles because it's continuous. Okay, and of course, continuous objects like the hammer will require integration. But our system of discrete particles isn't just going to be planets and asteroids and things like that. It can also just be particles, and you'll see examples in the notes where there's particle A, particle B, particle C, and we give the coordinates of each of them and the mass of each particle. So but this is a great way to first see how the center of mass is calculated. It's really an average of mass location. So what we're summing up here is the mass at, or the mth mass. So that's what m sub I would represent, and I'm just using the x center of mass as an example. So this would be the mth particle. Okay, and that's, excuse me, I misspoke there. That would be the mass of the ith particle. So the particle that has the designation I, and then I is going to be summed from 1 to n. So it might be the third particle, or the fourth particle, or the fifth particle, which is called why I'm calling it the ith particle. And then over here, this is just going to be the x location of that particle. So x location of the ith particle. Okay, And again, we're summing from I to n. It could be as few as 2. It could be as many as 5 or 6. Of course, as the number gets bigger, it's going to become impractical to do a discrete summation like this. The last thing to look at for our formula is that we are dividing by m, big M, and what big M represents is the total mass. Okay, so that would be m1 plus m2 plus m3 all the way up through mn. Okay, so the same thing applies equally to the y center of mass and the z center of mass. And we'll have cases where we'll have all 3 dimensions. We'll have many cases where we just have 2 dimensions. Okay, all right, so hopefully that formula all makes sense. So moving on to the next formula down here, this is simply a vector that points from the origin to the center of mass. Okay, so that would be the location vector of the center of mass. So vector pointing from whatever you define as the origin to the center of mass. So it's just simply taking the coordinates that we calculated either with the technique above or that we'll shortly mention with the technique below. But whatever way we calculated xcom, ycom, and zcom, well, now we can just attach those to an I hat, j hat, and k hat for their respective dimensions and then get a vector out of that information. Okay, so now we have how to find the center of mass for a continuous object. Okay, so this would be a continuous object. Okay, so you can see that the formula looks similar. What has happened, however, is that we've replaced the summation symbol. So we've replaced the summation symbol with an integral, because instead of summing over n particles, we're integrating over an infinite number of particles. Okay, and then likewise, we have the x is what we're integrating over, and instead of having mass of discrete particles, ith particles, instead we have a mass element, right? So the idea there is that the mass element is an infinitesimally small piece of mass. Okay, but the term that I really prefer, I think it's a good shorthand and gets the point across, is that term of mass element. So it's an infinitesimally small piece of mass. All right, and the same thing applies equally to the y center of mass and the z center of mass for continuous objects where we're using integration. The last formula that I will point out is one that takes the idea of the center of mass and includes it with motion. So it turns out that when you consider the velocity of the center of mass, that's what this is right here, this expression, okay, which of course is a vector, then you can express that vector as the momentum, the total momentum of your system of particles or your continuous object, more likely a system of particles. So the total momentum divided by the mass of each. Now you notice that this formula is not written in a general form with subscripts I and summing over n, but instead is only for 2. So this is the velocity of center of mass of a 2-body system, and then we'll just restrict it to that for the examples that we'll include in this class. So you could maybe imagine extending the idea, but you will not be asked to here in the class. So the velocity of the center of mass of 2-body system. Okay, but then continue on with the idea is it ends at the velocity of the center of mass is momentum, the total momentum, divided by the total mass. Okay, so this is the total momentum. And then we can see in the denominator that m1 plus m2 is clearly total mass because it's a 2-body system, and well, that's all the mass there is. But the important thing is that we can take that total momentum and split it up into individual momentums. So if you had 2 objects that were moving away from each other, for example, where maybe p1 points in the negative x direction and p2 points in the positive x direction, then you could have a case where the center of mass is just the sum of those 2 momentums, taking into account their directionality divided by the total mass. So perhaps if the momentums are equal to each other, right? So if p1 and p2 have the same magnitudes, but they were going in opposite directions, as I just mentioned as an example, then you can see that what happened is the numerator would become 0. And that means that you would have a velocity for the center of mass that would actually be at rest. But that makes sense because the system is remaining balanced if both pieces are moving away with equal momentum. They might not have equal mass, but they just have to have equal momentum. So kind of interesting idea, and definitely a nice inclusion of the topic of momentum, which of course was the main topic of chapter 8. Okay, and now we are going to move on to examples, which I will cover in the next video.